All right, thank you for everybody for tuning in. We're going to go over Autodesk Fusion Generative Design for manufacturing. My name's Mike Fiedler, and with me is Apollo Vanderberg. We're both enterprise simulation specialists here at Autodesk, and we're going to be the hosts for today's presentation. So just to give you a heads up on what the agenda will be, we're going to discuss what is generative design for manufacturing. We will give you a brief demo. Once we're done with those items, we will talk about what your next steps might be if you want to learn more or have somebody from Autodesk reach out to provide some more information. And we're certainly going to leave time for question and answer, which is probably our favorite part of the whole entire presentation. Give you an opportunity to ask any clarifying questions about either functions within the program itself or specifics about the next step. So I certainly encourage you when we get to that portion of the presentation to let us know any questions that you have, and we'll do our best to answer any of them. As we get into talking about the program and introducing you to the program, what I think maybe is smart to start with is, why might you care? Obviously, everybody cares, at least to some small extent, right? You're here in the presentation, but that could have been encouraged by somebody else. Take a look at this technology. It could have been your own. Let me see a little bit about what this is about. But we also think it's important to highlight that the program is a functional program available from Autodesk. People are leveraging it now in different industries. And so on the left-hand side there, you see the General Motors bracket, which you may have seen in some different publications. And in that case, they took a multi-part assembly and they consolidated it down using generative design into a single component. At the same time, that allows them to optimize the assembly for mass once we now have a single component. And then, of course, you can reduce the supply chain costs because we're taking multiple parts and reducing them down to a single part. So, potential reduction in the number of suppliers, certainly a reduction in the number of parts that need to be inventoried and stored somewhere. On the right-hand side, you see some generative design components on the wheelchair, and this was from a company called Disrupt Disability. And the idea there is to make the wheelchairs more versatile, to make them customizable and almost a fashion item, if you will, a unique design for the user of the wheelchair. And some of the benefits there is that it's able to be tailored to a unique person's measurements. So as this person grows, presuming that the disability starts out, at a younger age, then the components can be tailored for somebody that's, a lighter, smaller framed individual, and then be swapped out, as the person grows. And then, interchangeable parts based on needs, and whether that is, again, something to do with, the person growing, or whether it has something to do with change in particular needs as far as how they're perhaps using the chair. So I guess in a nutshell, just note that these are just two stories. There are many more stories out there as well about how different companies are leveraging the software today. So overall, what is the generative design technology? It's a design exploration technology, basically allowing you to simultaneously generate multiple CAD-ready solutions based on real-world manufacturing constraints and product performance requirements. And so basically what we're saying here is that you're going to get multiple CAD-ready solutions, based on the constraints that you input and based on the performance requirements that you input into the program. And that's really one of the primary objectives, or I guess the overarching objective of the software, right? When you normally start a task, you begin with a sketch, and then from that sketch, maybe you extrude it, revolve, cut, add fillets and features. really you're shaping what that design is based on, the constraints that you have been given. The idea with generative design is you input those constraints, you input that product performance requirement or requirements, and then the program generates numerous results for you, and then you can review those results and determine which one or two or three might best suit your needs. All right, so how does it help in your product development process? We're going to show this timeline here, and in a classic timeline, perhaps what you do is you start out with several different concepts, and those different concepts could be either thought of by you, or perhaps you get a small team of designers and engineers together and you come up with a number of different concepts. And then of course, from those concepts, you're going to take one and you're going to validate it. And when you evaluate it, maybe it's difficult or expensive to manufacture. So you go back and you take a look at a different concept, and again, you go through this process until you get one that's manufacturable and will suit the conditions, and then ultimately you're going to produce that one design, right? So you have a fairly lengthy iteration phase, and you have a somewhat lengthy design to production phase. And that would be your classic, start to finish process, development process. What we hope to do with generative design is upfront produce multiple validated manufacturing options. So you have a whole slew of different outputs that you can choose from. And then you pick one of these designs and produce this result. And you can see this swing arm here on the right-hand side. So we go from potentially a multi-part assembly that was iterated upon till you get to the final design, to having the program produce for you these multiple options, and thereby shortening both the iteration phase and the design to production phase. So if we overlay that with the classic methodology, what you should see there then at the end of it all is a productivity increase, right? Getting multiple designs faster and faster to production. To give an example of how the generative design contrasts with something like topology optimization, which you might be familiar with either from the simulation end of Fusion or perhaps within Inventor, we're going to use some sort of transportation analogy. So imagine that the process of designing your part is equivalent to this shipping route, right? And you know how long it takes to get from point A to point B. If you utilize topology optimization, what topology optimization does is basically makes a part lighter by taking your existing geometry and figuring out from this existing geometry where can we remove material. So, if we put this in terms of the shipping routes, it says, oh, okay, we can go through the Panama Canal. So that's a 60% faster route, right? So that's basically what topology optimization does. It says, I took your geometry and I made your geometry 40% lighter. You still have essentially the same shape that you had before. It's going to be the same material, of course. We're just going to make it lighter. On the other hand, with the generative design process, we're going to do that same thing, right? You can have a starting shape, or you don't necessarily even have to have a starting shape. But if you do, it'll certainly figure out how we can make that lighter. But at the same time, it's also going to give you different alternatives. Can we make this maybe by a 3D print? Can we use a milling machine? So there's different manufacturing methods involved as well. And at the same time, you can explore different materials. So in terms of transportation, that would be the same as including, for instance, a truck route, a train route, and a plane route. So what you see there on the graph in the upper or towards the right-hand corner is that, each one of these different methods is going to have different costs associated with them. They have different security associated with them, how much cargo they can carry, and the speed with which they do it. So Likewise, whenever generative design outputs the results of these different methodologies, the 3D printed versus something that is, say, using a 3-axis versus a 5-axis milling process, and the different materials, you're going to have different costs associated with them and different manufacturing speeds associated to them. With our next slide here, as we put this presentation together, at a more granular level, Apollo and I were thinking, well, what's the primary reasons that somebody might utilize generative design overall? And one would be new product design creation. And that's where, maybe you're coming face to face with a brand new product, and you don't really have at this point any constraints on how that might be manufactured or necessarily what that completely looks like, but where it might need to be constrained, what sort of loads it might need to carry. And in that case, you can certainly utilize generative design to ideate what that geometry is going to look like. And the second thing would be part consolidation. So maybe you currently have a multi-part assembly, and what you want to do is reduce that down to a single part, so that you have less parts to worry about and inventory. So it can also be utilized for that. And then a third reason that you might use it is because you have some existing geometry and you want to see, perhaps how do we lightweight this? What might it look like if we say that we're going to 3D print it, or we're going to use a different manufacturing methodology. So it could be any one of those three, or even a combination of those three. And then ultimately, given the utilization of the program, your goal, of course, is to strike the right balance between the performance and the cost to produce. So we know that engineers are limited in the time and energy that they can spend on any design. And of course, that's certainly where generative design is going to help out by producing multiple designs. All right. And then once you have all these different outputs, then of course, your objective is to balance the cost to produce with the performance of the particular outcome. So we're going to take a look at this in a hypothetical situation. If we lay out all these different outcomes that you get from generative design, at the one end of the spectrum, some of them might be lower cost, lower performance, and then at the other end of the spectrum, your high cost, high performance options. So, again, to use a transportation analogy, if we take a look at some different vehicles here, certainly these three different vehicles are going to have different costs associated with them in order to purchase them. As far as their performance is concerned, if we just fundamentally consider, am I able to go from point A to point B? Yes, they should all be able to do that, but how you get there and at what speed, what the experience is for the user, these are all going to be slightly different. So to put it more in terms of a engineering component, this is a bracket that was a component that was put forth by GE Aerospace some years ago, and basically what they asked was for input from the user community. If you were designing this part and they provided this as a starting shape and said this is where the constraints need to go within the 4 bolt holes, and then they provided different loads that needed to go onto the 2 lugs, vertical forces, horizontal forces, moments, how would you design this geometry? And the user community delivered. There was many users over some span of time. However, this challenge was open a month or 2 months, and they produced a lot of different designs. And it took, again, many designers a lot of different hours. And our intent with the generative design software is that we could produce a similar number of outputs, right, with one engineer, right? You as the designer or as the engineer are going to take this one design perhaps as your starting point, or even just some parts of this design. You could start with where your constraints are, where your loads are as preserve regions. You can put in your avoidance regions, which Apollo will cover here very shortly. And then the program is going to output for you a bunch of different designs. And then again, based on what best suits your needs, you can determine which ones you want to proceed with investigating further. All right, in this slide here, we just want to show that it's not necessarily restricted to brackets in a manufacturing environment, right? We see the ability to utilize generative design for different industries. So in the top left-hand side, you can see something like consumer products. And then towards the right-hand side of that, perhaps, yes, some more manufacturing industry related designs, the swing arm of the motorcycle, the braking system there. But then also things like industrial design. So if you look at the bottom row there, you see the housing to the light there, and towards the right-hand side there, perhaps some sort of shelving system bracket. So it could also be more towards the aesthetic end than just a lightweighting type of process or practice that you might go through for a typical manufacturing design. All right. So once you put in all the information to the program, where is this thing fixed or held? What are the materials that I'm going to utilize? What are the different manufacturing methods that I'd like to be able to potentially utilize? This is a snapshot of what you might get out of generative design. And you can see the plot here with all the different dots. So the different colored dots represent the different materials that they chose to explore. So 3 different materials, right? And then a number of different manufacturing methods, and these are all plotted out. And we can see that what we're looking at here is maximum displacement versus the mass. So that's the idea with generative design. It gives you numerous outputs, and then with these different outputs, you can pick different ones that you want to investigate further.
So let me step through a little bit what the workflow looks like before I go into a short demo showing some of the clicks and picks. So this kind of follows into what Mike was highlighting as maybe that third bucket, the part enhancement. So, we have a CAD model. We have technically we're going to look at the kind of suspension, A-arm, and we're going to try to see, could we make this out of other materials, and if so, what would that look like? How would that be manufacturable? Would that yield us any savings in terms of weight or cost? So from that CAD model, we'll project geometries. So there will be a need to have some pieces of geometry where we're going to assign the different loads for braking, acceleration, maybe the weight of the car, and then we have avoidance regions. So where we don't want any geometry to be built. So the suspension has to have some range of mobility that we need to keep clear. We might need access to making, putting in hardware like bolts. We need access for the tools to get to those bolts and mounting hardware. So all of that needs to be projected and then defined, including those load cases for what we're looking to represent. After that, we go into generate and let generative design, produce all of those outcomes based on those manufacturing methods that you're interested in and all the materials. And then finally, exploring it kind of as Mike mentioned, looking at it in a couple different ways. So we'll go ahead and step through here. So this is the A-arm that we're going to look at, in generative design. We're going to take this from the design space to the generative space. Here we can actually make unique edits to the model so it doesn't impact the actual production model, and project a number of features. So these will be all of our preserves where we're going to assign the different loads and constraints. As I mentioned, we need some sort of preserve. So this suspension has to rotate. There might be some frame members in here. We might need as well some avoidance regions for the mounting hardware that would go around the bushings, getting those bolts and whatnot. So once we have all of that built and projected, then we can go in and start actually defining this space. So picking those preserve regions, those that we want to keep We can select them, and as we assign them, they'll show up as green. In this case, we don't have a starting shape, so pretty much everything else that we have built is an avoidance region. We don't want any geometry built in it. But if we wanted to, we could leverage the existing design as a starting shape. And then from there, we want to build out all the different load cases. So, where are we constraining, the suspension? What are the different forces or moments acting on them in what orientations? And we can have, a number of different load cases. After that, we go into our objectives. So, what are we striving for? Are we trying to minimize mass, maximize stiffness? What's the safety factor we're looking for? And then what are those manufacturing methods that we're interested in looking at? Is it 3-axis or 5-axis? Since I've gone through making this video kind of highlighting the workflow, we've also added die casting and 2-axis cutting. What materials do we want to look at? So maybe this has traditionally been a steel component. Maybe we want to look at aluminum or some other metals, that could be either printed or CNC'd, and see if there is benefit to switching what we've been doing. We can go into make sure that the pre-check has everything in order and then generate all of our outcomes. So as we get our outcomes, we have all the thumbnail images there. On the left-hand side, we can isolate and filter based on the manufacturing method to see what they look like. We can filter based on, mass or displacement, different criteria and outputs to see which ones meet what we're looking for. We can look at it in tabular form, if that makes sense. I'd say a lot of people tend to jump more so into that graph that Mike was showing. So here we can choose the X and Y axis, and so we could see, hey, this corner here, which is looking at low mass and low displacement, maybe is of interest to us. All of those are orange ones are one material. This blue one is a different material. So let's take those two and compare them and see how they appear, depending on how they behaved. So in the compare, we can also look at the design space. So we can look at the stresses that are on the model. We can bring back those preserves and obstacle regions to see where they were. We can look at those specifics as far as what the factor of safety was that was achieved, what the displacement was, globally through the model. And then once we have one that we like, we can actually promote this back into design and Fusion, at which point we can either use it as is, or if we wanted to do further validation, we could take that into Fusion simulation, where we'll actually carry over all of those load cases into a preset simulation. So here, just kind of assembling it into the suspension itself. So that's just kind of at a high level, the workflow, what it looks like, how we can leverage it. Realistically, as a high level, that's kind of what we're trying to cover. Get your feet wet into it. Ultimately, people kind of ask, well, what's next? How do I dive into it? Maybe you've got a project in mind where this could be used. What I'd say is, so at the end of this webinar, as soon as we close out, there will be a short 3-question survey. One of those questions is if you're interested in us reaching out to you and having a further discussion, perhaps around that project, or maybe you have more specific questions than what you're willing to share here, to the audience at large. We're happy to dive in deeper. So just feel free to answer that question accordingly. And then one of the other questions is just, we're always looking for feedback on these webinars. Did this, kind of meet your expectations for what you're looking for and what drove you to this webinar versus, maybe some others. So, with that, what I'll say is, we can kick open Fusion here on our side and bring open a model in case there are specific questions, but we'll go ahead and open it up. So if you do have a question in GoToWebinar, you can use the questions panel, or if you'd like to talk out loud, feel free to raise your hand and we can unmute you. But yeah, the remaining time is for you guys, and yeah, any questions you'd like to dive in deeper with.
Okay, so we do have a question, and somebody said, what's the general cost for one case study? If there is only one iteration of a design, this is a cloud credit-based feature, correct? So you are correct, and that was something that I had in my head while Apollo was going through that demonstration, and he showed going to different materials and load cases. What I was going to say is right. It is cloud credit based, right? The number of cloud credits is based on running the simulation. Is that the right way which is that how you would put it? So the number of materials that you assign to it, the number of manufacturing methods that you assign to it, what other variables am I missing? Load cases. Those are all for, well, I don't want to say for free, but it's all in that token charge, right? So if you choose one material and say, give me the result of a 3-axis mill in the Y direction, it's the same charge as if you said, show me these 5 different materials and these 4 different manufacturing methods. So you know, if those are a possibility for you, if you say, I have, you know, these 3 different materials I'm willing to consider, and I have these X number of different manufacturing methods that we are able to consider, then I would go ahead and include them all in the analysis so that you get, you know, a larger number of outputs to explore, right? So then you're only charged for that token rate once, and you get a wider range of outputs, which are potential solutions for you to manufacture.
Yeah, so it kind of, in short, it is a flat fee with no additional cost if you add more materials or more manufacturing methods. All right, we do have one hand raised. As a follow-up, the flat fee, it's one flat fee per submission. So if you submit, you know, for design 1 per se, you go and submit the job to the cloud to run, whether you had 1 material or, you know, 10 materials, it's the same cost. Now, if you know, after looking at those results, you decide you want to make a change or you want to include additional load cases, and you go to submit it again, every time you click that generate button to generate outcomes, that's where the charge happens, and you'll be presented with that up front. So you know, you won't it won't just start solving and charging without your knowledge.
Right. And I think that you know, we should also maybe differentiate a little bit between load cases and different studies, right? So when you are doing a model, let's say that we take either the suspension, or you could even consider the GE aerospace bracket. And I don't want to get too, maybe we don't want to get too deep and confuse people here, but you know, you could say I have forces in the positive X direction. It needs to withstand a load of 100 pounds force, right? But then you probably also maybe have forces in the minus X direction too. You wouldn't necessarily want to put them on the same load case because they would negate each other. So you would have a positive 100-pound force, say in the positive X direction, and then maybe you have a minus 100 pounds force in the minus X direction. You would separate those into load case 1 and load case 2. So as it iterates through what this design needs to be to withstand those forces, it will compensate the design for both your positive x direction and your minus x direction as they are separate load cases. Those are not separate charges because they are still within the one submission, the one analysis. It's just considering, as it defines the geometry, what the geometry needs to be. I need to withstand the loads in load case 1 plus the loads in load case 2 plus whatever loads are in load case 3. So you can set up multiple load cases and it'll consider those in its outcome. It would only be when you set up a completely different design submission, if you will.
Yeah, it's a good question. So another one is, what is or are some of the limitations of generative design? And so, yeah, I mean, some of those limitations, you could say that we're, when we run those simulations, we are looking at, linear static stresses. So if you're getting into components that maybe are experiencing nonlinearities, that's where we have that workflow that I was kind of alluding to, where once you take a design that you like, you can promote it back into Fusion, so that you could leverage, say, Fusion simulation to look at some of the nonlinear aspects of the behavior of that part. So I'd say that's probably one of the limitations. In other cases, it could be maybe some of the loads and constraints that we have today. There are asks all the time for being able to assign more or different loads to the model so that people can be more accurate in what their component is experiencing, as well as additional manufacturing methods. So we release an update almost every 2 weeks with Fusion, and just in the past, I don't know, month and a half to 2 months, we've added in like 3 different manufacturing methods based on feedback and based on the community at large, looking to have more than what we had initially. So those would be the big ones. I'd say if there's something more specific that you're looking to understand around its limitations, it might be best to ask it in context to a part or a model, or what you're looking to do with it.
Yeah, that's one question that normally comes up as well, to expand or add something adjacent to what Apollo just said there. We do usually get some questions about analyses of the geometry, whether it's for vibrations or nonlinear or thermal. And when he exported or showed the export of that geometry, you're back in the design space. We would certainly love it if you stayed within Fusion. Fusion simulation does have a number of different analysis capabilities, including thermal and nonlinear, and some vibration. But given that you are in the design space now with your geometry, you can certainly export that as some type of universal file and take that if you have another FEA package of preference. I don't know, Inventor Nastran. Yeah. Okay. Keep it in the Autodesk family, but yes, you can certainly export it there. I would add as well.
Yeah. So I'll jump to this one here. Can I use generative design on single parts? How about multi-bodies or assemblies? So at this stage, yeah, I mean, we are focusing on we'll say a single part, right? As Mike presented or showed, that part could be the consolidation of a prior subassembly, or multiple parts, multiple bodies that existed, but the net output that we're generating is a single body, and what we're kind of bringing in, and even in terms of loading, as you kind of saw, is from that single part mentality. So we have those preserves that are are unique portions of what will become that final part. That is one of the things that I'd say I've heard probably the most is, perhaps trying to bring in a full assembly so that somebody could assign the loads to other parts of that assembly and just have, say like in this, the model that I went through, the suspension A-arm, perhaps bringing in everything from the chassis to the wheel, and so that you could assign forces at the wheel and at the chassis and have those transmit them accordingly to the A-arm. At this stage, you would have to do the math into what that A-arm should be experiencing for those different load cases, and kind of get your output.
Yes, but yeah, if you're okay with the output, so hypothetic, I don't know why you would, but let's say that just as a reminder, if that A-arm were currently, I don't know, 2-3 components that were bolted together, or at some point assembled together, yes, you could certainly take those 3 or however many components now and join them into, generative design is going to come out with its output will be a single component, right? So that goes back to what we were talking about consolidating assemblies into a single component. So if it's a matter of, you have a 4-part assembly that is currently either bolted together or welded together so that it makes a cohesive unit, and you're looking to see if the program can, given your constraints and loads, consolidate that into a single body and what that would look like. So that is certainly within the realm of the program.
Okay, one of the other questions here is, as a smaller company that might not have all the resources to produce multiple case studies per project, how do we utilize the software? It's a great design interface, but is it cost effective going through credits while trying to manage the learning curve? Yeah, that's an interesting one. That gets into a little bit more specifics, I'd say around, perhaps your company. When people do sign up with different entitlements, it's not uncommon that there are a small pool of cloud credits that are available to kind of get started. But beyond that, yeah, it depends on what you're getting into, and the realization of what Mike was showing, that time to market. If you look at your traditional methods that you have been doing before, how many different designs were you able to get in a given time frame, and how many were you able to validate? If you had a goal of always trying to look for 3 alternatives, then the overhead charge that you were experiencing in saving man hours might easily offset the nominal fee of just submitting the simulation to the cloud. So the act of solving it is the cheaper part, of being able to kind of get the insight and look at where geometry is required, and from there you can always kind of use that as a baseline to then design your own part, kind of in that ideate bucket that Mike was showing. Yeah, as far as some learning tools, to get started. So it's there are a couple different paths. One is probably in the last month we've updated Fusion to actually have a guided learning path built into the tool, and so you can definitely take advantage of that, and that'll walk you through some of the requirements. We also have the Fusion 360 Academy online, which has a bunch of content on learning all things Fusion. So it goes into modeling and to T-splines, but they do have a nice section posted there as well for generative, and kind of getting you up to speed with a couple tutorials. One of which I actually think is that GE bracket that we were talking around. So those would probably be for the masses, I'd say my starting point to learn it.
Yeah, and I don't think that our attendees here are off the mark, right? There is a, it's a token based or cloud credit based consumption model. I could understand that you don't want to just be throwing your cloud credits around wastefully, and I would wholeheartedly agree with Apollo that it probably makes sense. There, like he said, there's different layers of resources available, including the tutorials and the online academy. It probably makes sense to go through some sort of guide to begin with to kind of nail down the process. I think both of us, when we started with the program, as designers and engineers, we're envisioning things in our head about what that outcome looks like, right? So it's somewhat easy to think about what that final shape might need to look like. And maybe what we forget about is the obstructions, right? The regions that we don't want it to build in. Since you're giving the program the ability to construct what that geometry looks like, I think maybe that is one of the things that you get used to, but maybe is not something you think of right out of the gate. So going through a tutorial or watching some learning content helps develop that mindset, and then it doesn't take too long. I think afterwards to develop. You make that mistake once or twice and wait for the outcomes and go, oh shoot, it built where I don't want it to have built, and now I need to go back and make some obstructions.
Yeah, and some of that we're taking as people step through it, and changing the product even, right? So when we started with this, we had to specifically build every obstacle region that Mike's referring to, or avoidance region where we don't want geometry. But there are some commonalities in how people build geometry, and so now there is the ability, with like there's a button that allows you to pick a hole and kind of automatically create a bolt for an avoidance region, kind of referencing that there will be mounting hardware there. So kind of keeping that at the forefront, in your face, that you need to think about this. But even then, at times, it's not always even taking into account, say, tool access, right? So if you had a couple different bolts, throughout the geometry, like, can you get a wrench to that bolt, or can you get a socket there? How are you going to actually fix that bolt to through the hole itself? Is the bolt too long to snake through, to get to that mounting location? So some of those are we'll say the change in mentality that you'll start to come across as you go through reading some of the documentation and kind of going through those tutorials. So lastly, is it possible to program prerequisites such as minimum value of CD generated in the design? So if you're referencing the CD as far as like a drag coefficient, at this stage, I'd say maybe that goes back into the prior question of limitations. We're not looking at fluid flow. So if you're trying to, again, if we're looking at that A-arm, and this was for a performance vehicle, and we wanted to have minimized drag of that suspension component, we don't have we'll say fluid solid interactions, right? We're not doing FSI and seeing how airflow goes over this component and then extracting out to minimize or maximize a given output from that fluid side. Purely at this stage, this is a structural structural solver. It's doing structural analysis, and so yeah, there isn't anything on the fluid side that we can do. It is something that we are looking at and looking further into to understand what would be needed and what the ask from the industry is around that. outside of that, from a structural side, you know, what we kind of went through, and again, there's always more being added as far as the objectives, for the analysis. So are we trying to maximize stiffness? Are we looking for a specific factor of safety? Moving forward, we've actually added in costing details with our partnership with a priori to understand like what's the range of cost to manufacture that given part based on that manufacturing method and that material. So to get that, now there's even an input for what's the quantity that you'd be looking to manufacture, so that we can kind of get a better approximation there. Outside of those, there isn't a way to pre-program it in. You're kind of setting it up as you go through it each time. Is there a possibility to optimize the iteration of generative design for 3D printing? So yes, we have it listed as additive manufacturing. That is the manufacturing constraint that you would enable from a 3D printing perspective. You have a few details that you can specify there. So namely being like the overhang angle. So if you know that your printer can print up to a certain angle, you can specify that. And then by default, we will print in the positive X, positive Y, and positive Z directions. So kind of building off the platform in those three orientations. So if I, if you want real quick, I can kind of highlight that real quick with the video for a second. Let me jump ahead. So towards the end here, I'll let this play out again. There were a couple where this, given the orientation of this A-arm, when we did our additive print, it was assuming that we were flat on the print bed, and then we printed, vertically in this case, it was, in the Z direction to get that geometry. You don't have if you want to change the relative orientation, so if you're looking at, orienting this part for additive, you might have to change that location in your model prior to generating the outcome. So if you wanted to have like a self-supporting structure that was at some obscure angle relative to the planes, you would have to set that up in the setup process. But that's a good question. So any other questions while I wait for this video, just to get to that point, just to highlight the the additive outputs that we were showing. Yeah, so here, just to kind of go back to it, so here during the setup process, this is where you're picking, those manufacturing methods. When I did this video, I need to go back and update it to include now the die casting and, 2-axis cutting. But, this is where you're specifying, what the minimum thickness is for your parts, that you can print, and what the overhang angle is. So as you include this, we will, again, by default, assume we're going to do 3 outputs for additive in the positive X, Y, and Z directions from the build plane. Okay, and so here you can kind of see this is this one here is the additive, or one of the additive solutions. So kind of coming off of the build plane, we're trying to maintain a self-supporting, additive geometry, and so we're kind of filling it in to ensure that it's self-supporting and connecting to the appropriate, preserve regions. So since I had there were a couple different materials from an additive perspective, you get a couple different outcomes that are very similar, but maybe a little bit different based on those material properties. Let me see, I think there's another, yeah, that was probably the best image of it right there. So yeah, hopefully that answers your question around optimizing for 3D printing. All right, well, if there are no other questions, we'll go ahead and close it out. Like I said, if you'd like to dive in deeper, if you'd like to have a further discussion right at the end of this, as we end the webinar, there will be a quick survey asking you if you'd like us to reach out. Feel free to answer yes. If you answer no, thank you for joining, and hopefully we answered any questions that you might have had around generative design.
Yeah, thanks everybody. Good discussion.